Okay, to top off the course, I've decided to discuss abstract vector spaces and function spaces. Okay, so this would be a more complex extension of the ideas we discussed in the course. Okay, let's go. You can actually find this on Wikipedia here. A vector space V is a set closed under finite vector addition and scalar multiplication. Okay, basic example is n-dimensional Euclidean space. Okay, Rn. Okay, now you're used to that as a vector space. Okay, every element is represented by a list of n real numbers. Scalars are real numbers. Addition is component-wise, and scalar multiplication is multiplication on each component separately. Okay, don't have to worry about what a field is. I'm only going to discuss vector spaces over the real numbers and may mention the complex numbers on occasion. Okay, the point is to get a vector space, you've got to have a set of vectors, and then you've got a set of what? Real numbers or possibly complex numbers, but like I said, I'm going to focus on real numbers. Those are the scalars, okay, but you need to have those. All right, now they're designating their vectors here by capital Latinic letters. Okay, we've been having a different notation, but that's fine because we're in a more generalized context here anyways. Okay, what must the vectors satisfy? The vectors must have commutative addition. Okay, now they must have closure, by the way. I should mention that before anything else. So whenever I add two vectors, I better get what? Another vector back. So it still has to be in my vector space, right? For my set of vectors. Likewise, I have to have a scalar multiple closure, right? If I take any vector and multiply it by a scalar, a real number, I get a vector also, right? Or a vector that's something that's back in the vector space, so another vector. Okay, so you've got to have closure. Now for the addition has to be commutative. Okay, so it should not matter which order you add the vectors in. You should get the same resultant. The vectors better add associatively. Okay, there better be a zero vector that has this property. 0 plus any vector is the vector plus 0, which is the original vector. Okay, so you understand additive identity. Okay, so that's what we would be calling abstractly the zero vector. Okay, existence of an additive inverse. Okay, you don't necessarily have to use that designation, but this ends out from the properties of the vector space. There's going to be a unique additive inverse. Negative x plus x always has to give you the zero vector. Okay, you have to be able to do this. Okay, associativity of scalar multiplication there. Distributivity of scalar sums, so like you see there. Distributivity of vector sums. Okay, and notice, hopefully you're going through your mind as you're thinking about these, how Rn, right, satisfies all these. It does, doesn't it? Okay, for any n. Lastly, the scalar multiplication identity. If I multiply any vector by 1, right, the multiplicative identity, I should get that same scalar back. Okay, so Rn satisfies all those things. Okay, but it's not the only, the only example that you could come up with of a vector space. So a vector space is anything that satisfies these conditions, right? You got a set of vectors. Again, I'll just say over the reals, and the vectors have to satisfy these conditions here. Okay, let's talk about some other examples besides Rn then. Okay, for each n greater than or equal to 1, I'm going to talk about the set of all real polynomials in the variable x. Okay, of degree less than or equal to n. Okay, I'll denote it by this, p sub n of x. Okay, this forms a vector space over the real numbers. Okay, what are the vectors in this space? The vectors in this space are the polynomials themselves, the scalars being the real numbers. Okay, think about it. If I have two polynomials of degree that are less than or equal to n and add them together, I'm going to get another polynomial of degree less than or equal to n back. Same thing if I multiply any polynomial of degree less than or equal to n by a scalar, a real number. Once again, I'll get a polynomial of degree less than or equal to n back. Okay, Now you think about this, so I say there the closed under addition. What's the zero polynomial? That's the polynomial that's always zero, right? Okay, so that's the zero function, really. For all values of x, the value of the function would be, what, 0, okay? Or you could think of all of the coefficients being 0, making up the polynomial. Okay, that would be the additive identity, okay? The addition would be commutative, right? Going over the list of properties in your mind, see that it forms a vector space over the reals. I mean, come back up here. I'll come up real fast. Think in terms of polynomials as vectors instead. Does it matter what order I add these polynomials of degree less than or equal to n? No. Is it associative? Yep. Zero polynomial. There's an identity. If I multiply the polynomial by -1, I get an additive inverse. Yep. If I'm multiplying with real numbers on a polynomial, can I do this? So scalar associativity? Yep. Distributivity with the scalars yet? Distributivity of the polynomials? Yep. If I multiply 1 by a polynomial, do I get that same polynomial back? Yes. Okay, so these polynomials serve as a vector space, okay? What would be a polynomial, a basis for p sub n of x, right? Would be this, do you see? Every polynomial can be written as a linear combination of 1, x squared, out to x to the nth power, right? These would clearly span the space then, okay? Because every vector of degree less than or equal to m can be expressed this way, right there, right? I called it f of x. A naught through a n are real numbers, right? Those are the coefficients, okay? The zero polynomial, okay? The only way you get the zero polynomial is what? If all the coefficients are equal to 0, okay? So you can see pretty clearly this is an n-dimensional vector space, a real vector space. Okay, we can create an isomorphism between Rn and p sub n of x, okay? If I map I wrote this as a row vector transpose, so it's a column vector. So if I've got the column vector a naught through a n, okay, as part of Rn, and I map that onto what? A naught plus a1x plus such and so forth down to a sub n x to the n. Okay, I claim that would be an isomorphism. Remember, an isomorphism is a one-to-one onto mapping between vector spaces that preserves the operations. Okay, so for every vector u and v in Rn and scalar a and r, we've got the following. If I map phi, under phi here, if phi of u bar is p of x, some polynomial of x, right, and phi of v bar is q of x, then you can see what is true here, that phi of the sum of the two vectors in Rn would just end up getting mapped to the sum of the p and the q polynomials. Likewise, under that map up there, if I multiply any scalar on u, that would end up getting mapped to exactly a times p of x, okay? So there it is. So you could think of this as just being a funny way of writing these polynomials, right? You're just keeping track of the coefficients. Alrighty? So that's easy to verify that it's an isomorphism. Okay? Yeah, well, that's what we essentially did. Although these vector spaces are isomorphic, we'd say, okay, they look the same, they have very different inspirations, okay? Where did vectors really come from? They came from geometry, right? In fact, physical geometry, right? Okay, they were physicists and mathematicians. They were the same thing back then. They were thinking about what? Adding forces, for example, okay? And you would what? Add forces geometrically, okay? When you embedded those in as free vectors in a Cartesian space, what you were essentially doing is adding components, right? Okay, you were adding numbers in the various components in the column or row vectors, however you liked writing it, okay? So this was, Rn was inspired by geometry, while the latter, okay, p sub n of x, that's a function space polynomials, we think of them as functions, don't we? Okay? I would say this is also borne out by the different types of linear operations that would naturally come to mind in dealing with each. Okay, in the former, what type of natural linear operators do you think of in geometry? Things like what? That we had projections, shears, rotations. Okay? Now, you could always represent any linear operation or linear operator using what? A matrix product, right? Okay? But naturally, we thought of things like what? Projections, shears, and rotations. Okay? What kind of operations that might be linear would appear naturally if you were dealing with a function space like p sub n of x? How about derivatives, right? Isn't that a linear operation? Okay? Go back to the definition of a linear operator. You will see indeed that differentiation is a linear operation. Okay? In fact, I give this as an exercise for you. Show that the differentiation operator with respect to x, mapping what? The elements of p sub n of x into p sub n of x, is a linear operator. Go ahead and represent that as what? In Rn via the inverse as a matrix product. Remember, you can always do that. Remember, n is fixed there. Okay? But this is not something geometrically you would probably think of doing. Okay? You can do it. You can certainly create it, a corresponding operation in Rn, but it wouldn't be something you would probably naturally think of. But it's very natural in function spaces like p sub n of x. Okay, let's talk about another function space, another vector space over the reals, is C0 of x, okay? This is the set of all real-valued functions that are continuous over the real numbers, okay? So think of all functions that are continuous over the whole real number line, okay? Now, sometimes people might actually limit that, and I'll mention that a little bit later. Instead of just being continuous over the real number line, that might be continuous over the closed bounded interval from 0 to 1, or the open interval from 0 to 1, okay? Or something like that. But for now, I'll just say C0 of x, that is the set of all continuous functions from the reals into the reals. Okay? This time, once again, what constitute a vector is any continuous function, right? Okay? Any continuous function of the reals. Now, summation of continuous functions and scalar multiples of functions would be defined just as they were in college algebra. Remember when you used to add functions? What did you do? You just did it pointwise, right? For all values of x. Okay? So that's how you would add the functions in this space. Or you could think about scalar multiples. Very easy. Okay? It's also the fact, do you remember this in calculus, that the sum or scalar multiples of continuous functions is also continuous? Okay? That would prove closure, right? For the space under addition and scalar multiplication. The rest of it, like commutativity and so forth, for the axioms of a vector space, remember these guys, just to reiterate, all these guys can be shown to easily hold as well. Okay, so it wouldn't be hard, just kind of a drag, okay? But I just saw those are easily shown to hold, okay? I think you guys believe it here. Let's go back just for a second here. The vector space p sub n of x has dimension n, right? But every polynomial is continuous everywhere, so that's actually a subspace of what? C0, or C naught, even if you like that word, C naught of x. Okay, so that's a subspace. What is the dimension of C sub 0 of x? Okay, if you think about it here, it's going to be infinite. It's going to be infinite dimensional. Okay, we haven't really dealt with those before, and this is something you would deal with in higher level classes, okay? But my point is no finite collection of continuous functions would be sufficient to represent all continuous functions as linear combinations, and I think you guys could see that fairly easily, okay? Now let me mention what we've done here. We've generalized the idea of vector space from its original geometric foundation by just using the axiomatic method. What that means is You observe some properties that geometric vector spaces had, and you write those down, and then you declare an abstract vector space as anything that satisfies those particular properties, okay? We take those as axioms, okay, for forming our vectors, okay? Now, you take which ones are important, and the ones that people have found important over the years are those that I've listed originally, okay? But this idea of abstraction, generalizing an idea by the properties that something has, is so that your original just becomes a particular species of the new objects, can be done, this is done in mathematics over and over and over again, okay? Endlessly, okay? We can generalize the idea of dot product, okay? And I'm going to throw this in here, okay? People do this. With respect to, again, a real vector space, you can do all this stuff over complex vector spaces, but the definitions, it changes slightly, okay? But let's just say with respect to a real vector space that I'm calling V, we say that a function, this is actually a function here, notice that I'm just using angled brackets. That's typically what they use in functional analysis, higher mathematics, for an inner product, okay? It's a mapping from what? You take two vectors and you get a real number out of it. That's what this is saying here, okay? So this product here isn't cross product of vectors like you would with I, J, K, and determinants like that. This is something we would call the Cartesian product. This is just pairs of vectors. So it's just saying you take two vectors, and out of those two vectors you get a real number that is called the inner product of those two vectors, okay? Now, in order to be an inner product, the following has to hold. I'm assuming U, V, and W are arbitrarily chosen vectors in what? The vector space V. A is any scalar, okay, any real numbers. Here's what has to hold. The inner product of any vector with itself has to be greater than or equal to 0, okay? And in fact, the only way you can actually get 0 is if what? You are plugging in the 0 vector for U, okay? So that means any non-zero vector, the inner product with itself is always going to be positive. Here, it doesn't matter what order you take the inner product. Excuse me. This changes when you're talking about, it's complex conjugate when you're talking about complex vector spaces, by the way. But in real vector spaces, you don't have to worry about that. It's just saying inner product of U and V is exactly the same as the inner product of V and U. Okay, this is distributive also, okay? And you can bring a scalar out front here, okay? By the way, if you use the property number 2 in conjunction with 4, you could see if there was a B on this V, you could bring that out front also. In the complex case, that would be B conjugate, though. Okay? Anyways, but we're not dealing with that. So if these properties are satisfied for this what? Function of two vectors, real valued function of two vectors, U and V, okay? So U and V pop into it, and we usually write the inner product with angled bars, okay? If these are satisfied, we call it an inner product. The dot product, the usual dot product over the vector space Rn, is an example of an inner product, okay? It is an inner product. Again, the inner product is inspired by the dot product, okay? So the original critter, the original animal, is only one species of what? A whole new genus, okay? Here, let's take an example. A, by no means unique, inner product on the space C0 of x, or C0 of x, is given by the following way. Suppose I take the inner product of two continuous functions in the following way. I'm going to integrate from 0 to 1 of the product of the two continuous functions. Now that's going to be a real number, okay? That's going to be a real number, okay? If you think about it, you remember the product of what? Two continuous functions is continuous, and you can certainly integrate any continuous function over a closed bounded interval and get a real number out of it. You're right? Calc 1, okay? But if you do this, it might look crazy. Believe it or not, this thing, you could go through it. You could practice. You could do this for another exercise, EFY, exercise for you. Show that these properties are up here are satisfied, that this thing actually gives you an inner product. Okay? Is it true that what? The inner product of any polynomial with itself? So I would have p squared integrated from 0 to 1. Not polynomial, continuous function, which might be a polynomial. But from 0 to 1 ends up being what? Greater than or equal to 0 all the time. And the only way it's equal to 0 is if you plugged in what? The 0 continuous function, right? The function that's 0 everywhere. Okay? Is it symmetric? That is P inner product of P and Q the same as the inner product of Q and P? Okay, does it have these other properties? Yes. You can do that for an exercise here very easily. Okay? This would allow us to talk about certain sets of orthogonal polynomials. And they do that sometimes in differential equations. Okay? Sometimes in differential equations, they also include another little function in here called a weight function. Okay, W of x. There's another little function like to get Legendre polynomials and stuff. There might be a weight function in there. That's a non-negative function that sometimes people use. It makes things convenient here. But you could talk about what polynomials being orthogonal to each other and stuff like this. Okay, weird, huh? Okay, let's talk about an example of something like this happening. Here's a set of pairwise orthogonal functions under the inner product defined above. Okay, and you can show this, but I will mention it. Okay, so this is cosine of 0 pi, which is really 1. Cosine pi x, sine pi x, cosine 2 pi x, sine 2 pi x, cosine 3 pi x, sine 3 pi x, and so on and so forth. Okay, this is an infinite set, as you see. Okay. If you take the integral from 0 to 1 or the product of any two distinct elements of that set, you will get 0. Okay? So I wrote it this way, you see. Integral from 0 to 1 cosine m pi x cosine n pi x dx. That's going to be 0 if m and x are different. By the way, it's never going to be 0 if they're the same. Okay? And same thing, cosine with a sine, sine with a sine, and so forth. So these are orthogonal functions under that inner product that we came up with. Sounds goofy, huh? Well, it isn't. For example, if we confine ourselves, remember in the beginning I said we don't necessarily take the whole real number line? If we confine ourselves only to functions between 0 and 1, okay, so we're just interested in a function on a small interval, like from 0 to 1, then this leads to what are called classic Fourier series expansions. Okay, so we represent continuous functions. Okay, well, I tell you this idea is extended. It's more than just continuous. But continuous functions on the interval from 0 to 1, we can write them as linear combinations of elements from that set. And here's where I've done one for you. Okay, suppose I'm confining myself to x just between 0 and 1. Okay, that parabola, y equals x squared, actually has this expansion, 1/3 plus 4 over pi squared. The summation n goes from 1 to infinity, negative 1 to the n over n squared, cosine n pi x. Okay, notice how the signs didn't even appear in here. Okay, but the sine is an odd function. The cosine is an even function. X squared is an even function. Okay, well, that's really the clue is what's going on here. Okay, if you go further into differential equations, if you're in engineering or something, you will see this creeping back into your life for certain. Okay? All right, anyway, series of these kinds have applications in differential equations. That's crazy. You might, by the way, you might graph this in Desmos. You can't go to infinity, but you can take a whole bunch of terms. Take 20 of them. Okay? See what happens. Take 30 of them. See if it doesn't look more over 0 to 1. Of course, this is a periodic function, so you're going to get a periodic function on this side. except for the 1/3 there. Okay? So it's not going to be x squared everywhere, but over 0 to 1, it's going to be x squared. Interesting. Such series have applications of differential equations and also imply some pure, oops, I just spelled that wrong, mathematical findings such as the following. The summation n goes from 1 to infinity, -1 to the n over n squared. Remember Calc 2, us discussing about that. Comparison, absolute value test with a p-series, that better converge. What does it converge to? This is supposed to be pi over 12. Okay? Had a typo there as well. That's pi over 12. That's interesting. Okay? How about this? Another p-series, right? Okay, this was actually alternating series, right? So you didn't even need to compare it with the p-series. But it converges to pi over 12. How about 1 over n squared? That's a p-series with p equals 2. And that's pi squared over 6. Boy, I made a couple typos on this. Okay? Alrighty. And this is pi squared over 12. Not just pi over 12. There we go. Alrighty? Wow. This thing above implies each of these two with a little reasoning, believe it or not. That's pretty crazy, isn't it? Okay. In analysis, this notation Cn of x for n is between 1 up to and including infinity, okay, refers to vector spaces that are really function spaces, n times continuously differentiable. So these are actually functions that are n times continuously differentiable. Okay. Alrighty. These often occur in differential equations, in particular linear differential equations. Okay, so we're almost done here. A general nth order linear differential equation will look like this. Okay, remember that notation, superscript with parentheses around it, that's the nth derivative. Okay, so here we've got y as a function of x, and that is what? The nth derivative of y with respect to x, and so on. These coefficients are in fact functions. So I've got a subscript n minus 1 of x, y superscript n minus 1, so that's the n minus first derivative, so on and so forth, all the way down. Second derivative, first derivative, 0th derivative, so you differentiate it all. And we've got a function on the other side. Okay? This is the general form of the nth order linear differential equations. If you haven't had differential equations yet, then you may not be familiar with this. If you've had, then it certainly looks familiar. Under mild conditions, what would those be? Well, for example, continuity of the coefficient functions. The space has a general, the equation has a general solution that will consist of a function. Yeah, it's a vector space, but the vectors are really functions. So we'd like to say function space of dimension n. Exactly the same as what? The highest derivative that appears here. Okay? For example, be concrete about it. Y double prime minus 6y prime plus 5y equals 0. So I took a nice easy one here. It's even homogeneous here, meaning our b of x here is 0 on the other side here. Okay? This has general solution. Okay? Actually, it just struck me here. I better make this 0. Okay? I better make that 0 for that to hold. Okay, to actually be a function space. See, what you have is one particular, to get all solutions though, it's like working with a general plane instead of just a particular, oh, never mind. Anyway, just come on. All right, it has this general solution. Okay, this has to be 0 for that to actually be, yeah, let me finish it. Okay, this has to be 0 for this to actually be a vector space. But if you have one particular solution for, let's say b is not 0 there, if you just have that one particular solution, you just take that particular solution and then add what? All the possible homogeneous solutions, and you will get all solutions to the non-homogeneous differential equation there. Okay? All right. Anyways, this is homogeneous, so I can write this. This has general solution c1 e to the x plus c2 e to the 5x. Okay? You can see that that would be what? A function space, a vector space, actually. With what? Think of all these as being vectors. Okay? All right? You could see all the conditions for a vector space would be satisfied. Okay? C1 and C2 are arbitrary constants. This would be what? A vector space of degree 2, right? And that's what? Second order linear differential equations. Because the basis here would be e to the x, e to the 5x. Okay, just to show you where vector analysis and linear algebra starts appearing here in upper level mathematics here, okay? So we've barely scratched the surface of linear algebra in this class, and I guess that's the major point of this video. Okay, well, I hope you enjoyed this. I'm not going to test you on it or anything, but goodbye.